Hi everyone, welcome back to the video series for 2360. We're still talking about roots finding algorithms. We did one video of bisection already where we did the theory and the pseudocode. Let's do the same thing now for the second method, Newton-Raphson. Now, remember the goal of roots finding algorithms. We're talking about functions, some general function f of x, and we're going to say that f of x is equal to 0. So the goal, what we want is we want to know the numerical value of x, right? The numerical value of x, that when you put it into the function, it makes the function 0. So again, that's the root. We want to know what the root is of this function. So let's start just by plotting it, and let's do a general function. So here's our axes. We're looking at x on the horizontal, and we're plotting f of x here on the vertical. So here's the function. Function is doing something like this. And what we're going to do to get started with Newton-Raphson is we're going to pick one point somewhere on this curve. The closer we can get it here, we can see that the root is obviously right here. There you go, there's the root. If we knew what it was ahead of time, or if we get lucky and if we pick something close to it, that's going to make this algorithm work a lot faster. But in general, it can work regardless of where you pick it. There are going to be a couple of tricky places that come out of this algorithm, but we'll talk about those in a bit. So here is our function. What are we going to do? We're going to pick one point. Remember in the bisection method we picked 2, right? This time we're only going to pick 1. So let's pick a point somewhere over here. Let's say here's x1. So here would be f1. So you specify a point, right? The user picks this. You have some knowledge of the function. You know what the function is. F of x equals something. You plug in the value for x1, and you get the value f1. What we're going to do here at f1 is we're going to find the slope, the line that is tangent to the curve, and it's going to do something like that. And then we will extend that line all the way down until it hits the x-axis. So again, you picked x1, you went up to f1, you found the line, the tangent line at that point, and we extend it down here to the x-axis. This point where it crosses the x-axis, right here. If this is x1, this is now x2, and we're going to extend this down to the function. And here is f2. So what are we going to do? We're going to repeat this process, right? So just like here when we picked x1, we went up to f1, we found the tangent line. Let's find the tangent line here. So if I draw the tangent line here at this point and we extend it, we'll get something kind of like this. So x1, x2, that makes this point x3. We take this, we extend it up. Here is the function evaluated at x3 that makes it f3. And we're going to repeat this process. We're going to repeat this, finding the slope, extending this line through down to the x-axis, and finding new subsequent x values. We're going to repeat this until this process, this algorithm zooms in. This is x4 now. We're going to keep repeating this. And you can see, at least in this instance, as we repeat this over and over, we're going to eventually zoom in on this point right here on this root. So we're going to repeat this process. This explains it visually. Let's, where do we go from here? Let's sort out the math, right? Inside of the algorithm, we know we actually have to write some math equations. So while this makes sense, visually, graphically, let's sort out the math details, right? So we can write the algorithm. And second, we also need to talk about where this algorithm can go wrong. So let's do that real quick. We're talking about the Newton-Raphson method. Specifically, let's talk about what can go wrong with Newton-Raphson method. Two big ones. The first, what happens if you pick some initial conditions that are somewhere right here. Well, if we pick this point, right, if this is our x1, there we go. If this is our x1, then we're probably going to get some nice results out of this. We're going to find the tangent line, and it's going to cross down to here, and then it's going to zoom back, and we're probably going to be able to capture this right here. What happens though, what happens if we start picking points further up this curve? Each time that we pick a point further up the curve, remember that we have to evaluate the tangent lines, right? And we have to project the line now out here onto the x-axis. So as we get closer and closer to the very top of this curve, consider what is the slope at the top of this hump right here in the middle. Yeah, slope 0. The slope at this point right at the top, the slope is 0. There's the tangent line at the top of this curve. So what happens if you pick the top of this curve as your x1? Well, you're going to come up to this point, you're going to find the tangent line, and you're going to try to project it onto the x-axis, right? And it's never going to cross the x-axis. So we can see just visually that there is some problem, right? Something is going to happen in the algorithm when f prime of x is equal to 0. So if we say you pick some x value, and we know that you can evaluate the function, right? Here's the function f of x, and I'm saying the slope. If the slope of this function is equal to 0 at this point, then we have some problem. That's actually going to come out in the math, when we do the math in just a second. Here's the second point I want to bring up. What if we picked up this point over here? What if we picked this point? Did it again. There we go. What if we picked this point as x1? This is our new x1. This time when we find the tangent line, it's going to be something like this. And it's going to project down here. And then we're going to shoot up to here. So here is x2 now. We're going to shoot with x2, okay? Notice that in this case, at the x1, it actually took us away from the root. The root is over here, right? The root is to the left of x1. When I selected x1 and we solved for the slope here at x1, it actually pushed us to the right just a little bit. Now, maybe long term, if we run this over and over again, it'll get out of this little dip right here, right? And maybe this x2 will be enough to shoot it over here. But and just looking at it, x2 is going to land you somewhere right here. Hey, that puts you up here on the slope, and you're going to shoot down again. You can have problems with numerical algorithms. Newton-Raphson is one where you can have what's called right here at this point, this would be a local minimum. Okay, so we have some local minimum that your algorithm can get trapped in this minimum, and it can just bounce back and forth, and it can never get out and never actually find the root. So how do we avoid this problem? How do we avoid both of these problems? Really, both of these are avoided or controlled by your selection of the initial guess, x1. So if you have some function, you could run it multiple times. You could give it a whole range of input x1 values to see what you get. Another thing on that note is consider what happens if your function, what if it has multiple roots? So if here is the function and it's going to cross and it's going to come back. So there's our x-axis. This time now we have 3 roots. So we have the problem that arises when the slope goes to 0. We have problems associated with local minimum. And one more thing to keep in mind is that when you run this algorithm, it's only going to find one root. So if you have a function with multiple roots, if you want all of them, you have to run your algorithm several times. And this is a deterministic process. So if I give it the same x1 over and over and over again, x1, 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 and I keep doing the same algorithm, it's just going to find the same root. So you have to give it a whole range of x1s across some, we suspect that there are 3 roots in 0 to 1,000, something like that. So you pick some x1s, 0 to 1,000, you see if you can find those 3 roots. Okay, so this is showing some of the problems, and again, we're gonna see this one actually come up in the math. Let's do the math. We've looked at the Newton-Raphson graphically, right? Theoretically. We got an idea of how this is going to come together. Let's do a little bit of math, like a general case math, and see if we can put together some algorithm. And remember, what we're doing with Newton-Raphson is we would pick an x, right? We would pick an x1, we would go up and we would find a point, right? Up here would be your f1. We would do a tangent line, and the tangent line is going to go down to the x-axis, and then at this x-axis, here is x2. And this process is going to repeat, right? You would use x2 to go up and find some f2, maybe it's up, maybe it's down. You use the tangent line again to come back to the x-axis, and that leads you to a new x, x1 to x2, x2 to x3, x3 to x4, and so on. So really what we need out of this algorithm, what we really need is some way to go from x1 to x2, right? From x1 to x2, hopefully the root is somewhere in between, and then these two will converge, the window will get smaller and smaller, such that the difference between these eventually gets very small. Okay, this is what we need. We need to get from x1 to x2. So here's the information that we have to work with. We know the value of x1. We do not know the value of x2. We're looking for x2. I know x1, I know f1. I also know the slope, okay? Why would I know the slope? We're going to make some assumptions. We're going to assume that f of x and f prime x. We're going to assume that these are both known, okay? If you know f of x, that means given some x1, you can find the value of f1. Right? You have this. And then given some x1, if you can take the derivative of f of x, okay, that means you have f of x, that means you can solve for the slope. Good. So let's see if we can put all this together, and we need some way to solve for x2. Okay, let's start with an equation of a line. Here's a line segment. And I want the equation for this line. So let's actually do point, slope. Point slope form, back to middle school. And let's do a quick replacement. I'm going to take off f1. I'm going to call this point right here, I'm going to say that this point has coordinates y1, x1. So x1 is the horizontal, y1 is the vertical. Okay, so we need the equation for this line. Here we go. It is y2 minus y1 is equal to m x2 minus x1. So again, this is just general form, right? You've got two different points, x1 y1 and x2 y2, and then we know the slope. So here was y1, here's x1, here's x2. That means y2 is right here. Okay, so here's a general case. For the specific problem that we're trying to do, right? We're trying to massage out this algorithm. We can do some replacements here. For example, what is m in our problem? Well, we're saying that we know this information. That means we can replace m with f prime of x. Specifically, which x? We have x1 and we have x2. Well, it was the slope, right, evaluated at x1. So this is f prime of x1 and then multiplied by x2 minus x1. Again, x1 is the input, x2 is what we want. This is what we're trying to get. Next, what is y1? Yeah, this numerical value up here. Well, we have the function which makes y1 f of x, right? In this problem, what is y2? Well, we projected the line down to the x-axis, which means the numerical value of y2 is 0. right? This is, in this case, we're saying that y2 is actually 0. So let's just take this and let's put these claims in here. We have minus f of x equal to, bring this down, f prime of x, f prime of x1, x1. Yeah, don't forget these are x1s. And then here is x2 minus x1. Okay, we have this. Remember, we just want to solve for x2. Well, if you want to solve for x2, what are we going to do? Just divide by both sides, right? And then move the x1 to the other side. So we can say that x2 is equal to x1 minus, I've moved the x1 to the other side, that makes it positive, and then if we divide both sides by f prime, you're going to end up with negative f of x1 divided by f prime of x1. There we go. This is your Newton-Raphson update step for the algorithm. You input some value of x1. You can evaluate the function, f of x1. You can evaluate the slope, f prime of x1. And then that's going to give you the update, x2. We could also write this as more of like a general iteration. Let's say that xn plus 1 equals xn minus f of xn divided by f prime of xn. So now it's not just 1s and 2s, it could be 1 to 2, 2 to 3, 3 to 4, etc., etc. This is your update. This is the critical step in your Newton-Raphson algorithm. This is what is going to go inside of your loop. This is going to be your looping part. So given this, we have this understanding now of what has to be done. We know what we have to provide with the algorithm. We know what information we need ahead of time, right? So given all of this, let's write the pseudocode now. We've talked about the theory for the Newton-Raphson, right? We did the graphical approaches, we've done the math. Let's write up the pseudocode, and then you'll be ready to go off and solve the labs. Number one. Well, number one, the user has to provide some initial guess. Some initial guess, we're calling it x1, right? Remember on the bisection, you gave x1 and x2. Newton-Raphson, you only give the x1. Number two, we want to confirm that f prime of x1 does not equal 0. What we're talking about here is the slope can't be 0 at that point. Why can't the slope be 0 at that point? Well, because we're going to do an update step. So let's say update. So here's our update step, and we're going to say that x2 is equal to x1 minus f of x1 divided by f prime of x1. Remember, f prime of x1, this is the slope. We saw with the graphical portion, if we pick a point right here at the top and then we do the tangent line through it, if this tangent line, if the slope here, right, if f prime of x is 0, that means the tangent line is going to go off to infinity. Mathematically, what is that going to do? Well, the slope is here in the denominator. If this goes to 0, right, f of x, if f of x is 0, you've found the root, right? So we're going to assume that this is non-zero. So it's just some number, 5, right? F of x is 5. And let's say at this point, f prime is 0. Well, the limit of this is going to go to infinity. So you're taking x1 and you're add subtracting, right, whatever the sign is, you're add subtracting infinity to it, and that's going to throw off this math. Clearly this math is going to fail when f prime of x is equal to 0. That is the equivalent to what's happening graphically where you've picked the point where the slope is 0 and it goes off to infinity. This does also highlight, though, what happens if you pick the point just next to it. So the slope is not perfectly 0, but it is very small. Here in this math, we can see when this is a very small number, it makes this a very large number, and then x2 is significantly different than x1, right? You have shot off some very long distance, and it's going to take time for your algorithm to converge back. So we want to confirm that this thing is not 0. Hopefully it's not small either, but it definitely cannot be 0. Okay, so we've done, this is the Newton-Raphson update step number 4. Let's overwrite the value of x2. So we're going to set x2 equal to x1. All this is doing right here is we had x1 and then we went to a new x. We called it x2. We want to repeat this process, right, over and over until we can find the root. So all we're doing here is we're just saying, hey, take that, oh, wait a minute. x1, hey, sorry, okay. x1 is equal to x2. So we had x1, we went to x2, and now we're saying take that value of x2 and just overwrite x1 so that you can repeat this. Okay, so I'm going to say repeat until, and again, in all of these algorithms, we saw this in the bisection method, but in all of these algorithms, we have to specify when the algorithm is done, right? It's just going to run, and it's going to run inside of these loops that we put it in until we say stop. So when do we want this to stop? This right here, number 4. Number 4 represents the change in these, right? We had x1 and we had x2, and here at step 4, we're overwriting. When you go to do a check, what we want to do is right before you erase this old data, we want to take x1 and we want to take x2 and we want to subtract them. And we're going to take the absolute value because we don't care which one's bigger than the other. And then there's our epsilon. Here's our numerical threshold. You specify a small number, let's say 10 to the negative 10th. That is going to give you accuracy at 10 to the negative 10th, right? If the root is between these two, when the difference between these gets really small, that means it's very close to the correct answer. So here's the first one, right? So this is an actual convergence. We talked about, though, what can happen with these numerical methods, right? If you get an ill-tuned initial guess, right? Or maybe there's some local minima. Maybe you don't actually converge. So you're repeating this loop and this never gets satisfied. So let's add one more, and let's say we're going to repeat until we converge, or current number of iterations is greater than some maximum number of iterations. You specify, maybe this thing can only run 500 times or 1,000 times, something like that. So in case you get into a non-convergence or a local minimum problem, you can use this. You hit 500 cycles, congratulations, you're done no matter what. And then you would just come and print current value of x1, and that would be your final answer. Okay, so here's the pseudocode for the Newton-Raphson. What we're going to do next is I'm gonna put out some videos, some screen cap videos, where I show bisection method and Newton-Raphson both in implementation, so we'll get to see those in action. And then after that, we're gonna come back and we're gonna talk about Newton-Raphson for systems of equations. So I will see you next time. Good luck, stay safe.